Okay, so welcome. We're going to do our temperature notes. There's 4 sections to this. We're going to talk about temperature. We're going to talk about basically some thermodynamics. We're going to talk about, we'll talk about a particle in a box, what we call thermal statistics, and then we'll talk about heat engines. So there's 4 bits to this. Fair bit conceptual, there's some math as well. I ran into trouble with this because I didn't pay attention to the definitions. I was vague. And they introduced some new language, and I was vague about the new language. And then when they'd ask me questions, I didn't understand what they were asking. Although the equations were simple, I didn't know what to plug in where because they were using these what I thought were specialized terms, and I hadn't learned them. So watch out for that. So we're going to talk today about temperature and the zeroth law. Why on earth would you have a zeroth law? What if you were in charge of the world? Why on earth would you have something called the zeroth law? What circumstances would cause you to make a zeroth law? It's just the numbering. It's not the law of zero. It's just the, you have your first law, you have your second law, you have your third law. Well, they have a zeroth law. So, no, not that. No. It is, seems to me, it's fundamental, but we thought about it after we'd done the other 2. We had the first law, we had the second law, and people are still getting this wrong, so we need to have a law for this. But it's a simple thing, so we'll call it the zeroth law. This is goes before the others, And it is simple, but, when you read the definitions, in especially the old textbooks, man, it was so complicated. But I'm going to try and just make it clear to you. And you can see why they didn't think it needed writing down. But they did need writing down. So a zeroth law, we'll talk about temperature scales. And what we'll find out is that not all temperature scales are equivalent. Some are more useful than others. I've gone and just lost my place. And then we'll talk about thermal expansion. We have to put it in somewhere, so let's talk about it today. And then the macroscopic. If you do macroeconomics, you look at the economy as a whole. If you do microeconomics, you look at little bits of the economy. Same goes with this, the macroscopic model of the ideal gas. And then later on there'll be a chapter where we look at the microscopic model. So we imagine ourselves at a time before they really knew what was going on. And that's not that long ago, actually. Of all the parts of physics that you do in this course, this was one of the last ones to be kind of sorted out. There was more confusion about thermodynamics than there was about any of the others until really quite recently, 1850s. They were still trying to sort this out on a fundamental basis. They'd already invented the steam engine. It wasn't particularly good because they didn't really know how to think about thermodynamics, but they'd got the principle there. But they were struggling. And as we'll see, a guy called Lord Kelvin basically... Lord because of his services to science rather than, been rich and aristocratic. Lord Kelvin basically used his influence and said, we got to sort this out because it was holding technology back. Temperature and the zeroth law. Temperature is the direct measure of the average molecular kinetic energy. They did not know that until 1850s perhaps, maybe a bit later. They thought of heat and temperature as being a thing, and mechanics has been a completely different thing. And so they had some wacky ideas. They worked, but they were completely dead end. You couldn't keep with them. They had this idea about a caloric fluid. Things got hot because they got filled with a caloric fluid, and when they cooled down, that caloric fluid was leaking away. And you know that if you have a hot pan and the caloric fluid leaks away, it goes into the countertop, and you can feel the effect of the caloric fluid, which has fed into the countertop because it's warmer, and then the caloric fluid keeps spreading out, and so it gets less and less noticeable. You know, it's a way of thinking about it, completely, made up. If you can't find a particle and you keep looking for it, be a bit skeptical of it. Although we live today with particles we can't find, dark matter and stuff like that. We can see the effects of it, but maybe there's another way of thinking about it. So it's not that it's wrong, it's just it's sufficient for its purposes today. And the caloric fluid was sufficient for its purposes back in the day, but ran into trouble. So temperature is a direct measure of the average molecular kinetic energy. So think of the particle as in a solid as how much it vibrates, or in a fluid how fast it goes before it hits another fluid particle, or in a gas how fast it goes before it hits the container walls. It's that kind of thing. Two objects are in thermal equilibrium if no heat is exchanged between them, despite the fact that they are in thermal contact. The two objects must have the same temperature. A few terms there, we've got to be careful. Thermal equilibrium is basically I as an object I'm in equilibrium with this calculator. I'm not giving it energy, thermal energy. It's not giving me thermal energy. Well, in net, maybe I'm giving it as much as it's giving me, but there's no net flow one way or the other. That flow of thermal energy we give a special name to because it's important, and we call it heat. It's like your employer pays you money, but they call it salary. And when you go to the checkout counter, they don't say, give me my salary. They say, give me money, So salary is a name for money transfer under a very specific circumstances, because it's important. You don't want to get confused about wages versus just paying things out. So we give it a special name. Energy transfer from one object to another is important. There's energy in this, there's energy in me. The name we give for the transfer is special, like salary. We call it heat. So this does not contain heat, just like my bank account does not contain salary. I do not contain heat, just like my employer does not contain salary. I have money, my employer has money. When the employer gives the money to me, they call it salary. I have thermal energy, it has thermal energy. When I give thermal energy to it, it's called heat. If it gives thermal energy to me, it's called heat. That's a bit weird, but it's kind of like energy and transfer. So, all right, so two objects in thermal equilibrium. If no heat, there's no net transfer of energy is exchanged between them, despite the fact that they are in thermal contact. Thermal contact means I'm not just touching, but I'm touching and heat can flow. So if I had a big insulator surface, I would not be in thermal contact with this thing, even though I'm touching the insulator outside. It's not just that it's touching, but that heat can flow. Now, so if I am in thermal contact with this and no heat flows, there's no increase in my average kinetic energy per particle because no energy is coming into me. There's no increase in its average kinetic energy per particle because there's no energy flowing into it. So there's no increase in my temperature, there's no increase in its temperature. We must be at the same temperature. If we're not at thermal equilibrium, if it's got more kinetic energy per particle, heat's going to flow in my direction. I'm going to get more energy, so more average kinetic energy per particle. My temperature is going to rise. So thermal equilibrium is when, despite the fact we're in thermal contact, no heat flows, and that occurs when we're at the same temperature. So you can say thermal equilibrium, same temperature. Yeah? Two objects are in thermal contact with each other if heat energy can be exchanged between them. And heat is the transfer of energy from one object to another object resulting from difference in temperature between the two. So the zero flow states that two objects have the same temperature if they are in thermal equilibrium, and that's like so obvious, you know. But the way it used to be stated, very long-winded, and it seemed very complicated. It would say, I'm in thermal equilibrium with the monitor, and I'm in thermal equilibrium with a book, so the book is in thermal equilibrium with the monitor. What you're going to say is, I got the same temperature as the monitor, I got the same temperature as the book must have the same temperature as the monitor. It's obvious. You can see why they didn't think of writing it down. But when people start getting into this, it's easy to get lost, so you can see how they keep making that mistake. So, 0th law. Thermometers. Let's talk about temperature. Again, we're thinking before we knew what was going on. We need a way of measuring temperature in some systematic way. Hot and cold doesn't really do it. You know, ouch. Although they tried. People, before they had instrumentation, tried using their bodies as measuring devices. And some bizarre things got written. This guy was talking about basically jabbing himself with various spikes and gauging the pain that was caused as a measure of sharpness or force or something. And he started realizing that anticipation caused problems, because if he thought it was going to hurt, it really did hurt. So he said that he wrote things down before he thought about it, which, if you think about it, for a scientist to say, I wrote this down before I thought about it, is a little bit of a bizarre thing to say. But people tried it, you know. It was in the absence of anything else, what do you do? So people would go hot and cold, ouch, and that's hotter than that, and, you know, etc. But that's not a systematic way of going on. So people started saying, what can I see change because of temperature? And one of the most obvious things is that gas expands. It pushes more, balloons get bigger, or pistons get pushed up. So that's one way of measuring expansion of a gas. Another thing is, well, other things expand. Fluids expand. Solids expand. Some metals expand more than others, and so we can actually have tricks where we fasten two dissimilar metals together, and because the right-hand one expands more than the left-hand one, because they're screwed together at the top and the bottom, it forces that one round. That can be used to click a switch. That's a so-called bimetallic switch, and it works very nicely, actually. Used for years in water heaters. Used for years to turn your water heater on and off. It gets hot, and it turns off the switch, comes back, and it turns on the switch. It's just very nice. So anything. They'll use anything for a thermometer. When my granddad retired after 40, 45 years, 14 until he was 65, 50, 51 years working for the same company, apart from the general strike when nobody worked. For 51 years he worked for this one company, and basically when he retired they bought him a clock. It was this gilded clock in this glass dome. He hated it. When they first got it, they had this old wind-up clock, and they had it on the mantelpiece, and then they put the gilded clock there instead. And after a while, my granddad said, let's put that somewhere else. And it wasn't clear to me why, because it seemed look beautiful. And my mum explained that, you know, do you really want to buy a retiree a clock? I mean, what message are you sending them, you know? It's like, you know, and he just hated it. He wanted the old clock back, and, you know. So now they don't buy people clocks. Now I've noticed they buy them a thermometer. And they use this thermometer. We got one in the stockroom. The thermometer is basically a glass, I'll draw it here, glass column, and it's got liquid in it, and it's got all these little glass bubbles, and they're weighted so that it kind of like, there's a gap, and you can read the temperature from the gap, yeah? So, I mean, you know, it's not telling them you've only got a few more days left. It's kind of telling them, look at the temperature. It's like, man, just get them a Home Depot card, you know? It's like, my daughter's 13, and she said, I said, what do you want for your birthday? She goes, I want money. It's like, so obvious. I want money. But I could buy you something. I know you could, but I want money. So It's interesting things. They'll use anything. They'll use the expansion of a gas, the expansion of a fluid, the resistivity, the resistance of a metal. They'll use a weird thing called the thermoelectric effect, where dissimilar metals, junctions in different temperatures create a voltage. Who'd know? Who knew? You know? They'll use whatever they can to get a thermometer. The color that something glows with, not what it reflects, but the color that something glows with tells you its temperature. Usually we can't see those colors because our eyes are only tuned to the sun's temperatures, but you can make machines that look at these different colors. So a thermometer indicates temperature by displaying some physical property that varies with temperature. Typical physical properties include the volume, say the volume of a liquid or the volume of a gas, the length of a rod, the length of a column of liquid, the pressure, how much force it exerts, resistivity, and so it just goes on. There's so many different types of thermometers. But, however they do it, they're trying to measure temperature, and we need a numerical scale for temperature. And so there's two very common ones. There's the Fahrenheit scale, and there's the centigrade or Celsius scale. There's two names for the same thing. I remember as a kid in Britain, we used the Fahrenheit scale for day-to-day stuff, and we used the Celsius scale when we went to school to do science. And then a little bit after I left, they just got rid of the Fahrenheit scale, and they talk about Celsius. Temperature, while I was there, in fact, temperature. Room, 17 degrees, 18 degrees, 22 degrees is a bit hot. You go up to about 30 degrees, and you're like, you know, desert conditions kind of thing. People said they'll never get used to it. People get used to it. I was stunned by my brother, 5 years older than me, thinks completely metrically now. Just talks about so many centimeters, so many meters, driving at so many kilometers per hour, buying liters of gasoline. You know, but the only things that haven't changed are time hasn't changed, and actually beer hasn't changed. You can still buy beer in traditional pints. It's traditional, but they're the only two things. And my niece is just completely metric. So this idea that you can't change a population is not true. In America, ironically, in America now we have the Fahrenheit scale is for day-to-day use. But one of the few countries where that's still true. And Celsius scale is for the sciencey type stuff, you know. But that's... And I'm sure you guys, if you guys look online and stuff, you see centigrade temperature scale more often than I ever did. So where do they come from? Basically, liquid expands. You just have a column of liquid. As the liquid expands, you just mark it. And you just go, well, that's a temperature, and that's a temperature. And I'm going to divide it into however many steps I like in between. That's all you're doing. You're assuming the change is linear. If I go 1 degree higher, I'll get the same step. If I go 2 degrees higher, I'll get twice as big a step. If I go 3 degrees higher, I'll get 3 times as big a step. You assume it's linear. Not always true, in fact, but it's reasonably good. But the question is, where do you put your 0 and where do you put your, 100? And these two people, Fahrenheit and Celsius, are just two completely different ways of looking at it. Fahrenheit was interested in medicine. And so quite deliberately, he measured a healthy person's temperature, and he called that 100. And then he went and made a brine water mixture, and on the coldest day, he measured its temperature and called that 0, because it's never going to get colder than that, That's like. And he wanted to make it easy to deal with medicine, so 100 degrees is... And he wasn't far. Now we do a lot of averaging, etc. 98.7 degrees is like human body temperature. Except it's slightly different in Britain, apparently. It's 98.4 in Britain, I think, It's like, just the way it is. So it's not a crazy scale. There was a lot of logic behind it. The problem, the craziness came, and that later on people said, we can't have humans as one of our set points. What do? I have a whole bunch of humans in a cupboard and I bring them out whenever I want to check my thermometer. This is like craziness. I want something where I can actually do it in the lab and check it. So people said, why not boiling water. And why not water that's melting off of ice? Not the ice, but the water that's melting off of ice. Let's call that 0 and 100. This was Celsius. Celsius said, let's use the ice point as 0 and the water steam point as 100 and ice point as 0. The problem is that now people say, well, what's the ice point for Fahrenheit scale? It's 32 degrees. And then they go, well, why would you pick 32 degrees? And Fahrenheit goes, I didn't pick 32 degrees. I'm not interested in this point, but everybody else is. And then, well, what about boiling point? Well, 212 degrees Fahrenheit. You know, it's like, what? So it seems like the Fahrenheit scale was just, well, you know, the guy was just crazed. And he was very logical. He just was the first. And then along came Celsius, who said, what about reproduction of these tests? And so we ended up with that. Problem with the Celsius scale is that it's still a bizarre scale, because 0 degrees Celsius is not no temperature. It's just as cold as melting ice, as water melting off ice. And in New England, in Britain, you might not realize that because it don't really get that cold in Britain. But in New England, you'd know that straight away. It's like, man, it can be really cold, much colder than water melting from ice. And so what do you do with that? Well, you have negative numbers. And it works. 10 degrees difference is 10 degrees difference. 80 to 90 is the same as minus 60 to minus 50. It's just 10 degrees. Problem is, when you get to the definition, if temperature is the average kinetic energy per particle, how can you have a negative average energy per particle? It's like, what does that mean? It's like, it's just... But they didn't know that, but we do. And if the average temperature, average energy per particle is what makes temperature, there is a 0. You can stop those atoms from vibrating. You can stop those gas particles from flying through the air and hitting the container walls. You can stop those liquid particles from hitting each other. You can take them until they just sit there. And that's as cold as it gets. I don't know the temperature of the hottest place in the universe. I don't know if there is a temperature for the hottest place in the universe, because it seems to me I can always add more energy to it. But I can't take energy away from nothing. So there is a coldest, and it's quite accessible. And so what Lord Kelvin, William Thomson was his name, what Lord Kelvin basically said was, we've got to find 0, true 0 temperature. We've got to find out what it is. Because if I double my temperature, I have not doubled my average kinetic energy per particle. And that's a huge problem. I don't even know how much I've increased it by. I don't know what percentage I've increased it by. I just know I've increased it. So they did experiments a bit more elaborate than we did, where they took basically gas pressure and they put it in hot water and they put it in cold water and they put it in, ice water and carbon and brine, and they did what they could, went lower and lower and lower, and they plotted pressure versus temperature like we did in lab class, and they extrapolated quite a decent thing to do. And they looked pretty linear, so they just extended it, and they got down to here, and that was minus 273.14 degrees C. And Lord Kelvin said, let's call that 0 absolute, and just measure the same size as the temperature of degree C. Same unit size, same step size. We'll just work our way upwards. So 100 degrees C is 373 Kelvin. 0 degrees C is 273 Kelvin, and so on. So it cannot get colder than that. Nowhere in the universe. I can swear to it. It can't get colder than that, because you can't have less than no vibration. Like, so it's like, you're done. So that developed a new temperature scale, and it was actually, nowadays we call it the Kelvin scale after Lord Kelvin. A little bit of a nuance here. I'm always a little bit concerned when you go through to the next level, because there's these little, it's like joining a club. It is like joining a club. If you talk like an engineer and you walk like an engineer and you dress like an engineer, you're just assumed to be an engineer. And if you don't, then you're kind of excluded a little bit. You could be this maverick who's incredibly smart, who people go, oh man, that person's a maverick who's incredibly smart. And they'll respect you for your difference, but you've got to be really good for that. And even then, there'll be a bit of resentment because you're like not like us kind of thing, So language is important, and that's why reading the book is actually important. My notes are great, but they don't give you the language. So whenever you get the chance, read the book and try and use the language of engineering. And there's a few catches every now and then. Sometimes it's the foreign names. If you don't know how to pronounce them, people will go, oh, okay, don't know how to say it, So pay attention to that. I had a lot of trouble with that. The other thing is, there's these little catches sometimes, like it's traditional that we don't say degrees Kelvin. We don't say 25 degrees Kelvin. We say 25 degrees C. But we don't say degrees Kelvin. We say 25 Kelvin. We'll say that's a degree Kelvin because we're talking about the size of it, but we won't say 25 degrees Kelvin. And again, that's just like, it's one of those things where, oh, the secret handshake. Oh, you're really in the club, you know that. So it's just these little things. So watch out for that. So if you notice, I say just 0 Kelvin, 273 Kelvin, but I have this little degree sign up here, and in this case, it's not a typo. In this case, I meant it. If you want to go from temperature in Kelvin, it's just temperature in degrees C plus 273. Just add 273 onto it, vice versa. This other one's a bit more interesting. It looks complicated, but it's not that bad, actually. As a physicist, I go, well, hold on. If I have degree Fahrenheit and degree centigrade, there's my freezing point, here's my boiling point. That's 0, that's 100, that's 32, that's 212. Y equals mx plus b. Degree F is equal to my slope. It's going to be 180, 212 minus 32 over 100 degree C, plus my y-axis intercept, 32. And that's what I got there. I got 180 over 100, which is 9 over 5 TC plus 32. So I don't even remember that equation. I can just figure it out anytime I want. If you do a lot of it, you remember it, but you don't have to remember it. Cool? Conversions. Conversions. 1400 degrees C into, well, it's 1400 plus 273K, 1673, no problem. 66 degrees C into degrees F. Degree F is equal to 9 over 5 degrees C plus 32. Degree F is equal to 9 over 5 times 66 plus 32. My handy dandy little calculator. 66 times 9, enter, divided by 5, enter, plus 32, enter. 150.8. And then which is smaller? Well, the degree C is the same as the degree K. That by definition. Between ice and boiling water, there's 0 to 100. There's 273 to 373. That's 100 steps. That's 100 steps. There's 32 to 212. That's 180 steps. Which is the smallest division? Which one of these is smallest step? It's going to be A, isn't it? It's you need 180 little steps to get from there to there. You only need 100 to get from there to there. You only need 100 to get to there to there. So, yep. Visualization. Thermal expansion. If I am a matrix of metal, I got all my atoms lined up, and there's a little bit of vibration going on because they've got some energy. If I increase the amount of vibration, what happens to the spacing between these things? If I'm packed in a crowd and we're kind of like pretty close together, but then I start jostling and everybody starts jostling, what's going to happen to the volume occupied by that crowd? Increases. So things expand. Not everything behaves the same way for a given amount of energy. Some things express it a lot in vibration, other things not so much. There's more than vibrational modes to store energy. When I put energy into a solid, I put some of it into vibrational modes, but some of it goes into other modes that don't manifest as vibration. We'll get to that later. Different materials have different preferences. Like my wife puts most of her money into savings and a little bit into checking. I put most of my money into checking and a little bit into savings. If you judge our earnings by how much money we put into our checking, you get very different and incorrect answers. But I tend to do what I do and she tends to do what she does. So we're consistent to ourselves, but we're not the same. So aluminum might expand more per degree change than, say, now I can't think of a good example, tungsten, you know. So, and engineers know, physicists know that occurs, engineers know that occurs and know where to find the numbers. And it's not necessarily on Google, although Google's not bad. There's the engineering handbooks and stuff like that. There's reputable places, which Google will direct you towards. Rod's length changes with temperature. Usually the rod gets longer as temperature increases. The amount of extension depends upon the material, the temperature change, and the original length of the rod. So material, the temperature change, and the original length of rod. The coefficient of linear expansion is given by, let's have a look. Delta L is equal to alpha Li delta T. It's the change in temperature multiplied by the original length multiplied by the coefficient of thermal expansion gives you your change in length. And I can, maybe there's a better way to write this down. I think if we do delta L over Li is equal to, no, I don't want to do that. No, forget it. Okay. This also affects areas and volumes. For water, the coefficient of thermal expansion with temperature. So the water, oh yes, okay. Alpha has units of per degree C. If you rearrange this, alpha is equal to delta L over Li delta T. These lengths just cancel, so that equals 1 over delta T. Not in terms of dimensions, it's not in terms of numerical value, which is 1 over degree C, or degree C to the minus 1. If you measured it in K, it would be degree K to the minus 1, but degree C and degree K are the same thing. Degree F to the minus. If you measure it in degrees F to the minus 1. Cool. It's really the equation of a straight line. Yes. Yes. Okay. Cool. Let's have a look. Yes. And different materials have different ways. There's a wacky thing happens with water, and I'll get to that in a bit. Okay. At room temperature, brass ball will just fit through a hole in a brass plate. So here's the brass plate with a hole in it, and here's the brass ball, and it just fits through. What happens when only the ball is heated up to a significantly higher temperature? The ball will easily fit through the hole, the ball will just fit through the hole, or the ball will no longer fit through the hole. What do you think? Yeah, it's no longer going to fit. What will happen when only the plate is heated up to a significantly higher temperature? So, just fits. Now I heat the plate up. The ball will easily fit through the hole. The ball will just fit through the hole. That one's, I tell you that, it's not going to be that. There is a change going to happen. Or the ball will no longer fit through the hole. So why don't you tell the person next to you what you think? Just compare it. We've got a few minutes. So think about the critical point, which is the inner circumference of that ring. And then think about what expansion is and apply it to the inner circumference of that ring. Expansion.
Right. But it's expanding, meaning close to the hole.
Yeah.
So, imagine there are 6 atoms on this inner circle. And they move further away from each other. So, does that hole get bigger or smaller? It gets bigger, doesn't it? Now, hold on. Doesn't those 2 atoms get further away? Which means it gets smaller. The whole thing gets bigger. Yeah, it's like, it's really insidious. You know. It goes like that. So yes, the hole gets bigger and the plate gets bigger. And it's one of those things where when you can argue it both ways when you first see it.
To a small degree, though.
Yeah.
Like you're not going to be able to tell.
You're probably not going to be able to tell, yeah. And then don't worry about the last one. It's just me making up a stupid thing that's like you can't possibly answer. So this one is, it will easily fit through. Cool. Let's have a look. Let's do this, then we'll call it a day. Coefficient of linear expansion of the rod has the length of that. So here's my 30 centimeters at 40 degrees C and 50 centimeters at 45 degrees C. So what do I say? I say delta L is equal to alpha Li delta T. So delta L is my change in length, which is 50 minus 30 is equal to alpha, which is what I want to find. My original length, which is 30 times delta T, and that's 45 minus 40. So that's going to be 20 over 30 equals alpha times 5. So alpha is equal to, I got this wrong. No, it's not that. No, I got this wrong. I'm doing something badly wrong. Yes, I divided Li.
Oh, you didn't multiply the 30 times the 5 before you divided.
Oh no, I'm right. No, I'm sorry. I'm doing math wrong in my head. Alpha. So that's alpha, yeah. So alpha is equal to 20 over 5 times 30. Yeah, sorry. That's going to be 20 divided by 5 30s is 150. 0.1133 degrees per degree C. We're done. So let's just stop that. I'm sorry, I didn't mean to go on like that.